Olá a todos, estamos aqui em mais uma webinar, dessa vez diretamente da Itália para a Geotecnia Brasil, e eu trago hoje um convidado mais do que especial, o Gianluca Bella, diretamente da Itália. Buongiorno, buon apremedì, buonasera Gianluca.
Good afternoon, everyone.
Okay, so thank you very much for your presentation today. It's a big pleasure for us. This is your second presentation in Geotecnia Brazil, right?
Yes, of course. Thank you.
Everything is good with you?
Yes. Okay. When I can start, please let me know.
Okay, all right. So you can start your presentation. Thanks again, Gianluca.
Okay. Good afternoon, ladies and gentlemen. It's a very pleasure for me to be the speaker of this lecture, and thanks to you and to Felipe Cruz from Geotecnia Brazil for inviting me and for organizing this lecture. So, a short presentation. I am Gianluca Bella. I got a PhD in geotechnical engineer at Politecnico di Torino in Italy, focusing my research in the hydromechanical characterization, the static liquefaction, and the occurrence of the critical state condition of tailings under unsaturated condition. I also studied the aging of the same soil when I was visiting a researcher at the University of Minas Gerais in Brazil. Actually, I'm a geotechnical engineer at the ARCS Group company, dealing with the design of tunnels in complex conditions, retaining structures, foundation, monitoring, and slope stability analysis. Finally, I am actually lecturer in geotechnical engineering at the University of Applied Science and Arts of Southern Switzerland. The scope of these lectures is to show you the main experimental outcomes obtained on the tailings collected from the Stava dams that collapsed 40 years ago, where the static liquefaction was supposed to play a relevant role. Here, the structure of the current presentation. After the introduction, in the first part of the lecture, I will provide you with some basic concept about the unsaturated soil mechanics and the static liquefaction. Then, in the second part, I will show you the main experimental results obtaining carried out monotonic triaxial test on the Stava tailings. Their susceptibility to static liquefaction was experimentally investigating by analyzing some factors such as the sample preparation technique, the initial density, and the degree of saturation. I will conclude my lecture with a numerical example where the above concepts were used to perform a stability analysis of an ideal tailing dam. Finally, some conclusion and remarks will follow. Okay, so let's start with the introduction. Well, tailings are the waste products resulting from the chemical and from the mechanical separation processes of mineral extraction, comprising of mixtures of crushed rocks and processing fluids. Their particle size range from sand to clay silt sites, and their production in the last years is constantly growing. As you know, tailing dams represent some of the largest and complex geotechnical structures in the world. These structures usually comprise of a raised edge embankment constructed in a stage over the life of the embankment, and a basin aimed to store billions of tons of tailings material. According to the classical hydraulic segregation profile, a higher permeability zone made up of coarse particles would exist near the embankment, the discharge point, with a lower permeability zone made up of fine particles farthest from this point. And between them, there is an intermediate permeability zone, the beach. Okay. Why is the stability of a tailing dam is a relevant issue. I try to analyze some causes. Well, tailing dams are complex structures. They are particularly devoted to failure for the following reason. They are made of heterogeneous filling material. Dams are raised step by step over a large period of times, many years. Sometimes there is some poor regulations or poor specific design criteria, even if in the last year the regulation make a great advancement in many countries. And their large surface makes punctual criticality identification so difficult and would require extensive and continuous monitoring and cost times consuming. So why is relevant? Why is the stability of tailing dam a relevant problem, a relevant issue? First of all, because the collapse of these structures may result in fatalities, in several economical and environmental impacts, as shown by recent failures in Brazil, in South Africa, and so on. We can see that the annual tailing growth is estimated about 12 kilometers cube of tailings, and the total number of every tailing dams, I mean active, inactive, closed facility, is very high. With 8,500 is 800 and 500 with 270 kilometers of cube of disposed tailings, and this quantity would be enough to fill a cube 6 kilometer high, so very big quantities. And then overtopping, static liquefaction and dynamic liquefaction are the most frequent causes of tailing dams collapse, as we can see in the picture on the left and on the right. A list of the main causes of tailing dams failures. There are many failures that can contribute as a combination of various factors to lead a tailing dam to fail. First of all, a poor design, then a lack of maintenance. Failure can be due to seismic activity or hydraulic loading, foundation instability, erosion phenomenon, slope instability, compact and consolidation can be as another cause of tailing dams failure, piping and seepage, structural failures, compartmentalization failures, or human error, and regulatory and oversight lapses. But what I would like to focalize with the lesson of today is the saturation of tailings. In fact, if tailing materials become overly saturated, they can lose the shear strength and cohesion, making them prone to slumping and causing instability in the dam. And finally, we have a change in water content as one of the main causes. In fact, seasonal fluctuation in the water content within tailings can impact in the embankment stability, particularly if the dam's drainage and water management are not working effectively. Okay, so now we can go with some basic concepts about unsaturated soil mechanics and static liquefaction. As we can see in these pictures, tailing basins are heterogeneous and complex systems subjected to many external factors affecting their operation. For example, the amount of surface runoff, the infiltration rate, the consolidation process, or the capillary rise, as shown in these pictures. This factor, caused by the interaction with the atmosphere, govern the position of the phreatic surface within the basin, leading to variation in the height of the unsaturated zone above the water table. the unsaturated condition mainly involve a large portion of tailing dams, in particular shallow layers, because they are involved in water exchange with the atmosphere, such as surface runoff, infiltration, and so on, and involve also deep soil layers above the water table, where the capillarity phenomena can occur, especially for the finer soil fraction, leading the creation of a thick portion of soil under unsaturated conditions. Above the water table, we have the so-called vadose zone, or a capillary zone, in which the capillary rise occurs because the soil pores act as capillary tubes. Due to the capillarity, we have an ascent flow of water within the capillary tubes, and this rise basically depends on the diameter of the capillary tubes and other things that are constant when we deal with higher water systems. The smaller the capillary tubes are, the higher the capillary rise is. Therefore, imagine the soil as a group of capillary tubes having different sides. At different heights above the water table, there are tubes that will gradually desaturate. So, there is a zone immediately above the water table where the saturation is still total. Then there is a zone where the degree of saturation gradually decreases and then becomes zero at a height distance from the water table, as we can see in the central pictures. Contextually, we introduce the variable used to describe the pressure within unsaturated soil, which is the matrix suction. It is the negative value of pore pressure. Above the water table, the pressure are negative, and thus we have a positive suction that increase with height. And then we have the osmotic component of the total suction that I see it is made of matrix and osmotic component. The osmotic component, it is related to the concentration of salts in the porosity water, and it is related to phenomena of chemical interaction between the salts and the double layers of ions around the clay particles. Okay, so unsaturated soil can be assumed as a medium made of soil, water, and air. The effect of suction for unsaturated soils are the following. First of all, an increase of the normal stress between particles. Second, an increase of the shear strength. And finally, a decrease in the sliding occurrence. Moreover, we can say that there is a coupling between hydraulic and mechanical behavior in unsaturated condition. And on the right picture, we can see a flow chart for the stability analysis under unsaturated condition. Okay, we can proceed with with defining the shear strength. And the concept of static liquefaction. The shear strength of a saturated soil depends on its effective stress according to Moore-Coulomb criteria given in the top equation. Now we can define the static liquefaction. According to Sladen, liquefaction is a phenomenon in which a soil mass temporarily lose a relevant part, a great part of its shear resistance when subjected to monotonic, cyclic, or impulsive loads, and it flows as a liquid. Recently, Olson defined static liquefaction as a complete loss of strength that occurs when the pore pressure of a saturated soil equals the mean total stress, bringing the effective stress to zero. As a consequence, when a soil liquefies, it behaves as a fluid since it has no temporary shear strength. In the picture on the top, we can see the definition on the state parameters, very useful to the static liquefaction. This parameter was proposed by Bean and Jeffries in 1985, and it is defined as the difference between the current void ratio and the void ratio at critical state. If this parameter, I mean this difference, is positive, the sample is prone to liquefy, meaning we are dealing with a loose sample prone to show contractive behavior, and vice versa. And in the pictures on the bottom, we can see the definition of the liquefaction potential. We can see that it is given by the ratio between eta and the mu, where eta is the ratio between the deviatoric stress and mean effective stress. The liquefaction potential values close or above 0.7 indicate a high liquefaction potential and the possibility of the stress path turning to the left due to the pore pressure rise and drastically reducing the strength of the soil. The static liquefaction is correlated to tailing dams. Yes, the answer is of course yes. And the static liquefaction, for instance, due to heavy rainfall, is one of the major cause of collapse of tailing dams, leading the higher numbers of tailing dam failures in the world. It is worth remembering some consideration made by eminent researchers about it. Davis said that among the failures of tailing dam, the static liquefaction is the most common, but also the least well understood phenomenon. And some years before, Fourier reported that in the past, many tailing dams failures have been wrongly attributed to other causes, and the role of static liquefaction has not been recognized as one of the leading collapse factors. So we can conclude that the number of collapses that occurred in the year indicated that the mechanical behavior of tailing at the moment it is not clear to a sufficient number of designers. So why tailing facility are complex geotechnical systems particularly prone to failure? Guaranteeing the stability of such impoundment is, of course, one of the most challenging tasks in the mine waste management. These storage basins are in fact prone to failure for static liquefaction for the following reason. First, they are made of locally derived filling material, soil, coarse, waste, overburden material from mining operation. The second, dams are raised step by step, as I said before. Three, sometimes there is a lack of regulation, and of course there is some difficult to identify punctual criticality. With reference to the in situ scale, we can say that for a contractive soil, the static liquefaction could be induced by fast variation in the total stress under undrained condition. For example, erosion of the dam 2, collapse of the foundation, excessive dam rising rate. And more in general, the liquefaction can also be caused by change in the hydraulic condition of the site. For example, increase of the phreatic water table caused by unusual rains, snowball, or failure collapse of drainage systems. And how can we study the static liquefaction from the experimental point of view? In the previous slide, we see the static liquefaction from the in situ scale. Now we try to define the static liquefaction from the laboratory point of view. If the trigger is an external load, the static liquefaction can be studied by performing consolidated triaxial test with shearing under undrained condition, while a constant shearing triaxial test, CS, under undrained condition can be performed if the trigger is the increase in the pore pressure under constant total stress. So there are different ways to study the static liquefaction in laboratory. Finally, some case history of a failure due to the static liquefaction. The Wachusett Dam at the beginning of the last century was the first example of a static liquefaction collapse, but it was not recognized at that time. Other famous example of failure due to the static liquefaction is the Calaveras Dam in 1918 in the USA, and this is an example where the static liquefaction was identified for the first time. Then after that there was many other collapse, famous collapse. For example, the Maritzburg gold tailing dams in South Africa in 1994, or the Mount Polley in Canada in 2014. So we can, from these slides, we can say that a deep knowledge of the hydromechanical response of tailings under unsaturated condition represent a fundamental aspect to perform reliable stability analysis of tailing dams. After having introduced you some concept of unsaturated soil mechanics and static liquefaction, I can approach the core of these lectures, and this part deals with the experimental study of the static liquefaction susceptibility of a real case, the Stava tailings. What I will show you, the experimental investigation, the experimental result, has been published in different papers, as you can see in these pictures, published with my my colleague Professor Guido Musso from Politecnico di Torino, and also with other researchers. So we can move forward. The soil under investigation is the silty fraction of tailings from the lower portion of the Stava upper dam, built one above the other on a natural slope near the municipality of Stava. We are in Italy. The two tailing dams were gradually raised to store the waste products coming from the separation process of the Prestavel fluorite mine. On the 19th of July 1985, the upper tailing dams collapsed on the lower one, which in turn failed, triggering the static liquefaction of the storage tailings. A very huge quantity of tailings, a big mud flow, spilled out at a speed of about 90 km per hour in the Stava Valley, and mud flow killed 278 people, causing huge environmental and economical damage. Poor drainage, high phreatic levels, and the unconsolidated state of the stored tailings are supposed to be the main factors that lead to static liquefaction and so to the failures of the dam. Before showing you the experimentation to investigate the static liquefaction response of Stava tailings, it's worth to note that the same soil was previously characterized over the years by myself and by other researchers to investigate also other aspects different from static liquefaction. The first study was carried out by Carrera about 20 years ago. He performed basic odometer tests and triaxial tests on Stava tailings under saturated condition. She what she observed. The clean sand is subjected, as we can see in the picture on the top right. The clean sand is subjected to liquefaction only for very high void ratio. The sand mixed with about 30% of fine and 50% of fine both reach the liquefaction at a lower void ratio than the clean sand, and the mixture 50-50 liquefied at the lowest void ratio. The silty simple liquefied at higher void ratio than the 50-50 sample and the 70-30 sample, but still a lower value than the sand. So in every case, the void ratio at the liquefaction is in the range, lies in the range between the maximum and the minimum void ratio for each material, which are very different. So a comparison among different materials cannot be properly done considering only the void ratio, but it should be done by considering its position with regards to the extreme max and minimum void ratio. The graph show that the sand must be in a state very close to its maximum void ratio. For instance, the relative density has to be very low to reach liquefaction if compared to other mixture. While the 70-30 sample and the pure silt can liquefy at the void ratio which are halfway between maximum and minimum. So from this observation, it can be concluded that the sandy material is less prone to liquefy than the other material. After Carrera, there were some other research. In particular, I studied the research performed by myself in 2017 at Politecnico di Torino. I performed water retention tests by using a suction-controlled odometer to investigate the water retention response of the same soil. The retention properties of Stava tailings were found to largely depends on the void ratio, and such a dependency was interpreted through the expression of Gallipoli, obtaining the water retention curve given in the right. Carrera in 2008 carried out an extensive experimental investigation to define the shear strength of the same soil under saturated condition. And some years later, I performed additional investigation by using suction control triaxial test to mechanically characterize the soil under unsaturated condition. And on the right, we can see the critical state line with the experimental point, the red one, the saturated sample, and the black, the unsaturated sample. So we try to characterize both in unsaturated and saturated condition the shear strength of the soil. Moreover, together with my colleague of the Applied University in Switzerland, we performed some additional tests by using a conventional odometer to investigate the compressibility response of the Stava silty tailings in unsaturated and saturated condition. So we estimate the compressibility of the soil at different suction levels. Now, let's come back to the current experimentation, the focus of these lectures to investigate the static liquefaction of Stava tailing in unsaturated condition. Some monotonic triaxial tests were carried out on reconstituted sample, 38 mm initial diameter and 76 mm initial height. They were prepared at a different initial void ratio and water content. Two sample preparation were adopted. First of all, an external compaction was the technique used to prepare sample 1 and 2, and the moist tamping method was the method adopted to compact sample from test 3 to test 8. The moist tamping technique was adopted to reproduce one of the most common deposition procedure of tailings into the basing. On the right, there is a pictures of the triaxial cell. Is a Bishop and Westlake triaxial cell used in the experimentation performed at Politecnico di Torino in Italy. Here, there is a list of the tested sample and their initial state in terms of preparation method, initial void ratio, and water content and dry density of each tested sample. The triaxial tests were carried out by following these phases. First, partial saturation of the sample, involving the flushing phase and the back pressure phase, in order to get the Biscampton parameters less than 1. I mean, we obtained from 0.89 to 0.99. Then it followed an isotropic consolidation of the sample, reaching a mean effective stress equal to 80 kilopascal, and finally was applied a strain control shearing under undrained condition at constant radial effective stress. And then back analysis was performed to analyze the real properties of the tested sample. In these pictures, in the table, we can see the void ratio at the final consolidation phase, the degree of saturation reached by each sample at the end of the consolidation phase, and the matrix suction, the minimum and the maximum value of the matrix suction estimated by using the water retention curve that I show you some slide before. And in the last column, we can see if the sample liquefy or not liquefy. During the B-check and during the consolidation, wetting was caused by the decrease in the sample volume, not accompanied by any identical decrease in water volume. As the void ratio decreased during all of this stage, the position of the main branches of the water retention curve evolved as well, with a general increase in the air entry value and the higher occlusion value. For each test, the suction attained at the end of consolidation was unknown, and however, it must lay within the range given by the suctions which, introduced in the Gallipoli equation, together with the specific volume of the sample, predict the degree of saturation determined at the end of the consolidation. By the way, for example, figure on the right provides the main branches of the water retention curve and the degree of saturation and the limit of admissible suction range for test 3 and test 5. Now we can go to the to the results of this experimentation and to comment the results. The effect of the preparation technique on the hydromechanical behavior is investigated, since this aspect might represent a different deposition method of tailings inside the basing. The stress paths of 3 samples are shown in the figure on the left. The samples were prepared by means of the moist tamping method, sample TXT number 4, and by the external compaction procedure, sample TXT7 and TXT8. Despite their degree of saturation being similar at the end of the consolidation, they exhibited different stress-strain response, as we can clearly see from the graph. Indeed, the loser specimen TXT7 and TXT8 show an hardening behavior, while test TXT4, even if denser, approach the steady state by means of a softening response. The stress path of a sample TXT4 plotted in terms of mean effective stress and pore water pressure allow to identify the instability line. This difference can be appreciated in terms of excess of pore pressure developed during the undrained shearing phase. The excess of pore pressure of sample TXT4 reached a value of about 78 kilopascal, and then it remained constant, the green line. On the contrary, the excess of pore pressure of sample 7 and sample 8 reach a peak value, about 70 kilopascal, and then decrease, the red solid and dotted line. Such a response is a consequence of a transitional behavior of this sample, which at a large axial strain exhibit a stress hardening behavior. These results lead to conclude that the preparation method strongly affect the mechanical behaviors, since it lead to different soil fabrics. In fact, we can see that the denser sample, but prepared with the most tempered sample, exhibit a contractive behavior, despite sample are loose, that sample prepared with external compacted method are looser, but do not show a contraction behavior, but show an hardening behavior. So I repeat, the preparation method is very, very important to define to observe the behavior of the sample. Now we can see some literature evidence of the influence of the preparation technique on the static liquefaction. The above result on the Stava tailings that I show you in the previous slide are in good agreement with the literature. On the left, we can see the effect of the preparation technique on the mechanical behavior of some sandy tailings. On the right, we can see the stress path followed by gold tailings having similar initial density, but different preparation technique. In both cases, the most tempered specimen were the most prone to liquefaction, showing a softening response followed by static liquefaction. Now we investigate another aspect, that it's the influence of the void ratio on the static liquefaction. The effect of the initial density on the stress strain response of Stava tailings was investigated. As shown in the figure on the left, sample 1 and sample 3 were prepared by the same technique, the moist tamping technique, and both had a degree of saturation about 0.98. But their void ratio at the end of the consolidation were different because of different volumetric strain that occurred during the flushing step. Despite this difference, the two samples show the same mechanical response, as we can see in the picture, deviatoric versus axial strain. A very similar response was observed also for sample 2 and 6 in the picture on the right, which also had a different initial density but the same degree of saturation. And it might therefore be concluded that over the range of degree of saturation and within the void ratio explored the value of void ratio as a negligible effect on the behavior. So we have similar hydromechanical behavior over a certain high void ratio. The third aspect we investigate is the influence of the degree of saturation. So, the effect of the degree of saturation on the hydraulic and mechanical behavior of tailings was studied for moist tempered samples. The void ratio at the end of consolidation phase for test 1, 4, and 5 was very similar, but their degree of saturation was different as shown in the figure on the left. 0.98 for test 1, 0.94 for test 4, and 0.89 for test number 5, the red line. Sample 5 show a maximum deviatory stress higher than those experimented by sample 4 or 1. The residual value of the deviatoric stress of sample 5 was about 30 kilopascal, twice the one of test 4 and test number 1. These results seem to suggest that in the context of Stava tailings, a degree of saturation below about 90% is sufficient to significantly reduce the softening. These results are in good agreement, in accordance with the experimental outcomes obtained from soil shared by carrying out monotonic and cyclic tests from other authors. If the maximum excess of pore pressure developed during the undrained shearing phase of each test is divided by the effective mean stress, the evolution of the ratio excess of pore pressure and mean effective stress with the degree of saturation can be observed as shown in the figure on the right. A contractive behavior at high degree of saturation was expected, but because of the undrained condition, sample 1, 2, 3, and 4, and 6 were not allowed to contract, leading the pore pressure to increase and so leading the loss of the shear strength. On the contrary, on the other side, when the degree of saturation of the unsaturated sample is below 90%, and this is the case of sample number 5, the developed excess of pore pressure is much less than that of saturated sample, leading to higher strength also for loose sample that could be prone to liquefy because of its initial density. A preliminary interpretation of these experimental results provided in the previous section could be given by considering the relationship between the big Skempton coefficient and the degree of saturation. Defining the Skempton coefficient as the ratio between the excess pore pressure and the cell pressure. Under the hypothesis of an elastic and isotropic behavior of all the components, the experimental BSR points were fitted by the Reus equation, properly modified to consider a soil skeleton made of interconnected pores filled with two fluids, water and air. The elastic response of air and water was assumed to be due of homogenized fluid, which bulk modulus, Kf, was evaluated by considering the modulus of the two phases depending on their volume fraction. Under such an hypothesis, the Bishop equation was modified and a good agreement between the experimental points and the theoretical BSR curves was observed also for Stava tailings, as shown in the picture on the left. In undrained condition, when the degree of saturation slightly decreases below the unit, for example, due to change in suction, the B value and in turn the excess of pore pressure were proved to be much lower than that in saturated condition, leading an increase in the soil shear strength and so strongly influence the occurrence of the static liquefaction, as shown in the pictures. Here we can see an analytical mathematical passage to derive the above BSR relationship, but for a matter of time I would skip this part. But of course, I'm available for any detailed clarification for which person are interesting. Just send me an email and we can go in detail of these formulations, of course. The experimental point BSR relationship were also fitted by by using the model proposed by Lade and Hernandez, where UWV was the pore pressure at each saturation step. This is representing in the pictures on the left. Finally, a comparison between the value obtained by applying the lower radius limit relationship, the Lade-Hernandez relationship, together with the experimental BSR, is given in the right, in the picture on the right for test number 1, showing again a good agreement with all these relationship. I'd like to conclude with a preliminary interpretation of the exposed behavior of Stava tailings with an interpretation within the frame of the critical state theory. It's worth to remember that the critical state is a condition in which, as the formation proceeds with shearing, volumes of soil tend toward an ultimate state in which shearing strain can continue without further variation or volumetric strain, deviatory strain of mean effective stress. In unsaturated condition, no variation of water ration are also expected within shearing strain. Within the framework of the critical state, the susceptibility of a soil to liquefied is related to the state parameters, as I told before, proposed by Bean and Jeffries as the difference between the void ratio E and the void ratio at critical state, EGS, under the same mean stress. A positive value of the state parameter is related to loose specimen prone to liquefy, while a negative value of the state parameter is related to dense specimen with a dilatative behavior. The critical state line derived from the final condition of triaxial test performed by Carrera on saturated sample is given in the picture on the right by the solid line. In the same figure, the critical state line associated with unsaturated sample tested in other experimental campaign by means of suction control triaxial test is provided, and it is the dotted line for suction level ranging between 30 kPa and 45 kPa. In the same compression plane, the initial state of a Stava sample tested in the current research is given by the red symbols. Fully symbols refer to the nearly saturated sample 1, 2, 3, 4, and 6, and so refer to the solid critical state line in fully saturated condition. They lie above the critical state line, and so they exhibit liquefaction with a softening response. On the other hand, the empty red triangles refer to the unsaturated sample number 5. With reference to its initial state, it should be associated with an unsaturated critical state line well below critical state line having suction 30 kPa and close to the one of saturated state. Therefore, in principle, it has a positive state parameter, but as we saw in the previous slide, it did not show liquefaction since the pore pressure increased during shearing. This can be explained considering that as the degree of saturation decrease, the induced overpressure decrease as well as previously detected from B parameter SR relationship. On the other hand, the pore pressure increase developed during test 1, 2, 3, and 4, and 6 was large enough to bring this sample to liquefaction, as confirmed by the experimental result previously exposed. Finally, this larger pore pressure increase can also be explained in terms of reduced compressibility of the pore fluid mixture and by the evolution of the B parameter with the degree of saturation. So, what are the implications of the above result? For instance, we can preliminarily estimate the shear strength of the soil to be used in stability analysis. So, the static liquefaction of Stava moist tempered sample was evaluated by means of the Ishihara equation. The strength of the residual strength of the unsaturated sample number 5, the red symbol shown in these pictures, results about 2 times greater than that of nearly saturated sample 1, 2, 3, and 4, and 6, as shown in these pictures. After having introduced you some concept of soil mechanics, some major results obtained from experimentation in unsaturated condition, I would like to show you in a very short time a numerical example. Okay, this application is taken from my recent paper published for the National Conference of Geotechnical Engineering Researcher. We studied the influence, from the numerical point of view, the influence of the degree of saturation by using the material point method, in particular Anura 3D code, that is a large strain continuum, that use a large continuum strain approach. The liquefaction occurrence was investigated, was studied by considering a simplified approach in terms of undrained shear strength that is related to the saturation degree of tailings. The geometry of a tailings storage reproduce the section of an upstream configuration with a slope 2 on 3 on the external side, while the subsequent upstream dikes built on the top of progressive deposited tailings have an average slope about 1 on 3. For the secondary dikes, the starter dams and the foundation soil drained strength parameter are considered, and the more Coulomb failure criteria is considered in this simulation. We suppose 3 scenarios: HP, LP1, LP2. That means high phreatic surface, low phreatic surface 1, and low phreatic surface number 2. And these scenarios are considered to investigate, to study the impact of different undrained shear strength on failure behavior associated to different level saturation degree of tailings. We estimate the cohesion, the friction angle for tailings having a different degree of saturation, as you can see in the table on the right. So for different degree of saturation, 98%, 89, 83, and so on, we estimate the cohesion and a friction angle. We perform simulation, so by simulating the position, the three positions corresponding to the three scenario of the phreatic surface, by imposing, of course, the properties corresponding to this different degree of saturation. And first of all, the three scenarios, HP, LP1, and LP2, show a similar failure mechanism at the beginning of the simulation, time 10 seconds, with a similar shape and slightly lower plastic strain for LP compared to the HP scenarios. If we consider the evolution of the failures, I mean the figure on the bottom, it's possible to appreciate great different runout distance for the three scenarios. The contours of the final displacement for HP, LP1, and LP2 show the effect of the progressing lowering of the initial water table. With the increasing value of undrained strength, the propagation of tailing downstreams tend to reduce, with the maximum final displacement equal about 300 meters for the scenario of high phreatic level, and reducing to 215 and 191 meters for the scenario with lower phreatic surface. This response find an explanation if we see at the kinetic energy of the system with the time. The scenario with the high phreatic surface show a significantly higher peak in kinetic energy if compared to other two cases, meaning that larger velocity characterized this first scenario. This result supports the importance of maintaining low water tables in tailings basins with efficient drainage systems, and therefore highlighting the importance of continuous monitoring the pore pressure distribution within the basin during the construction, during the operation, and after the closure of the tailing dams. So I would like to conclude as follows. The static liquefaction has been recognized as one of the major causes of tailing dams collapse. Tailing dams interact with the atmosphere, of course, and to account for the possibility of static liquefaction, also in undrained condition, analysis should be able to reproduce the pore water pressure and the degree of saturation in the vadose zone. This lecture, this research, present an insight in the hydromechanical behavior of the Stava tailings in unsaturated condition, with a special focusing on the static liquefaction response. We investigated some factors affecting the static liquefaction, in particular the preparation technique, the soil density, and the degree of saturation. The influence of the preparation method was investigated, while externally compacted sample did not show tendency to liquefy. The moist tamping sample were more prone to liquefaction, even if they are started from void ratio and water ratio lower than use of externally compacted sample. So the preparation technique strongly influence the mechanical response because it leads to a different soil fabrics of the sample. The influence of the soil density, I mean the void ratio, was also investigated within the degree of saturation and the void ratio investigated. The increase of density in this case has a little relevant effect on the mechanical behavior of the Stava tailings. The pore pressure increments developed during the shear phase was related to the sample degree of saturation. That is the last factor we studied. Smaller degree of saturation lead to smaller overpressures. In the explored range, degree of saturation either 10-89%, the relationship between them was found to be about linear. Since the overpressure decrease as the degree of saturation decrease, the tendency to liquefy also decrease. In the moist tamping experiment, softening almost didn't occur for sample with a degrees of saturation about 90%, while it always occurs for higher degree of saturation. And the degree of saturation of about 90% seems to represent a limit below which the liquefaction does not occur. Finally, a simplified numerical application is presented to investigate the effect of the degree of saturation on the failure initialization and failure propagation. Here you can see the list of references used for these lectures, some PhD thesis, mine and Carrera thesis, some papers, and some websites. I wish to thank Geotecnia Brazil. I would like to extend my thanks to Felipe Cruitz from Geotecnia Brazil for making this lecture possible. And I would like to thank all my co-authors of some papers whose results have been presented in these lectures. And of course, thank you all for your attention. If there are any questions, I would like to respond and to keep in touch with you, and you can write me an email, and we can exchange idea or concept. Again, thank you all for your attention.
Okay, Gianluca, thank you very much for your amazing presentation. Can you send the papers for me, please?
Yes, of course. I can send you the paper for you. Yes, Tiago, it's a pleasure.
Okay. Another point, you show some results from MPM. You use Anura 3D, right?
Yes.
Why you use Anura? We have another options for sorting. Why did you choose Anura?
Anura 3D was used in this simplified study to simulate to study the propagation of the failure depending on the degree of saturation of the soil. To study the propagation, the evolution of tailings failures, of tailings, sorry, imply large displacement, large strains that, of course, cannot be studied by using finite element codes that deals with small strain and small displacement. So Anura in this case was selected. There are also other software that can be used for this purpose, but was selected to study the propagation of tailings under different saturation state.
Good. In Brazil, in general, we use it to discrete element method. Okay.
Yes. Okay. The FDM. Yeah.
And it's a good way to compare MPM with them, right?
Yes, it is. Thank you for the observation. It's very interesting, and I agree that it could be a very good. It will be an interesting comparison. The use of these two code, of course. I think one can easily reproduce the geometry I created, importing the properties, and see what happens in terms, of course, of runoff distance. Yes.
Okay, good. We don't have time into another question. So thanks again for your presentation and see you later.
Thank you all, Tiago, for giving me also you this the opportunity, and I hope to see you again, all for maybe for another lecture.
Yes. Okay. Bye bye.
Okay, thank you. Bye bye.